In this video, we're going to look at a harder example involving the singular value decomposition. So let's find the singular value decomposition of this 4x2 matrix. So I want to give you the opportunity to try this first. So pause the video for about 5 minutes to try this. So 4, 3, 2, 1, pause the video. Pause the video for about 5 minutes to try this. So I'm giving you 5 minutes because these SVD problems, they can be kind of long and kind of tedious. So we really need a decent amount of time to get into this. All right, so hopefully you've done that. Hopefully you've paused the video and it's been about 5 minutes for you, but just a few seconds for me. So to begin this process, the first step would be to find an orthogonal diagonalization of A transpose times A. So I've gone ahead and worked out what this is. So A transpose times A ends up being just a diagonal matrix, 6, 0, 0, 6. So the eigenvalues, because this is triangular, in fact it's diagonal, this is triangular, which means the eigenvalues are on the diagonal. Eigenvalues are along the diagonal. That's why they're the 6. It's 6 and 6, it's repeated. So now let's find the eigenvectors. So for 6, we would form A minus 6i, but A minus 6i is just going to be 0, 0, 0, 0. So that we have a matrix of just all zeros, which means both of the variables are free. Both x1 and x2 are free. So we end up getting 2 eigenvectors. So one eigenvector is 1, 0. That's coming from the fact that x1 is free. And the other eigenvector, v2, would be 0, 1. All right. So I've skipped some steps there, maybe just 1 or 2 steps, to write down these 2 vectors. So I'd want you to verify and make sure it makes sense how I got these, how I got v1 and v2. All right, so that's the first step. We need to find our eigenvalues, we need to find our eigenvectors. All right, so we are on to step 2. So now we want to list the eigenvalues in descending order and then find their corresponding singular values. So we have 2 eigenvalues, 6 and 6, just a repeated eigenvalue. So the singular values are the square roots of these. So sigma 1 is going to be root 6. And same thing with sigma 2, it's going to be the square root of 6. All right, so we have our singular values. So that was pretty quick. All right, so we are on to step 3. Now let's form the matrix V. So we need to construct the matrix V that has those eigenvectors v1 up to vn in order where the ith vector in this matrix corresponds to the ith greatest eigenvalue that we got. And this is an orthogonal matrix, which means the columns need to be normalized. All right, so when we form V, those vectors that we got earlier were already normal, which is kind of nice. In fact, they were the standard basis vectors, 1, 0, and 0, 1. Usually that won't happen, but we kind of got lucky here. All right, so in this first column, this corresponds to our first singular value, sigma 1, which was root 6. And the second column corresponded to the next singular value, which was also root 6. So we are ready for step 4. We're going to find sigma next. So step 4, we want to construct sigma. So recall that sigma has this form, where in the upper left corner, it's going to have a diagonal matrix, an R by R diagonal matrix. That'll consist of all the non-zero singular values along the main diagonal, and then everywhere else in the matrix, we're going to have zeros. So now, in our specific example, so before we write down what sigma is, recall that sigma needs to have the same size as A. And in our problem, what was the size of A? So if I flip it back to the previous page, what was A's size? I think it was a bit lower. Here we go. So A was 4 by 2. So sigma needs to be 4 by 2. So sigma needs to be a 4 by 2 matrix. Okay, so I'm going to form a 4 by 2 matrix, so it's going to be more narrow. Okay, and then I start off along this main diagonal, putting my singular values. So I have putting my non-zero singular values. So I have root 6, and then the next one is root 6 again. So at that point, I reach this sort of far bracket. I can't go beyond this. All right, so now we're going to form the diagonal part. So that's sort of the diagonal matrix D. And everywhere else in the matrix, we put zeros. And that's our matrix sigma. So in this example, everything here on the right-hand side of this sort of bar that I drew wasn't in my particular matrix. And sometimes that'll happen. Sometimes there will be these extra zeros to the right of the diagonal matrix, or sort of diagonally down and below it. But in this example, it didn't happen. All right, so we got our matrix sigma. We got our matrix V. We are on to step 5. So step 5 is typically the step that can be a bit more tedious. Of course, finding the eigenvalues and the eigenvectors can be tedious as well. So I would say that step, eigenvalues and eigenvectors, as well as this step where we find U, are typically the more time-consuming steps. So we want to construct the matrix U. And U has this form. So 1 over sigma 1 times A times V1, this is the first vector of U, U1. And then we keep going like that up until the rth vector. So U1 up until UR, we can find using this formula here. So they're going to be 1 over the corresponding singular value times A times VI, for whichever I we're talking about. So that's going to be true up until we get to VR. We can do this. Okay, and then the last columns after that, so UR plus 1 up until UM, they're going to be chosen in such a way that'll ensure that U has orthonormal columns. And once we do that, then we're ready to write down the singular value decomposition. All right, so let's start by writing the first columns of U. So let's start with the U1. So U1, so we're going to be able to use this formula for U1. It's going to be 1 over sigma 1 times A times V1. So the first singular value was root 6. And then times the matrix A, which was 1, 1, 2, 0. And then negative 2, 0, 1, 1. That was the matrix A. V1 was the vector 1, 0. That was the first column of the matrix V. So if we work this out, we will end up getting 1 over root 6. 1 over root 6. 2 over root 6. And 0. So we end up with that. And we could check that this vector ends up being a normal vector. This has length 1. And that's good. That's what we'd want it to be. All right. So for U1, we got to use this formula to figure out what it is. I get to keep using that formula until I get to UR. So in our problem, R equals 2. Because there were 2 non-zero singular values. And we allow repeats. That's why it's 2. All right, so we're going to be able to do the same thing to get U2. And I've gone ahead and done that already. So U2 is the following. So I work out the same type of computation, and I end up getting this vector here. So one thing to notice is when we use this formula, this formula that's 1 over sigma I times A VI, the corresponding UIs need to be orthonormal. So in particular, they need to be orthogonal to each other. So notice that U1 dotted with U2 is 0. That's a good check to do. Anytime we're using this formula, this 1 over sigma 1, A times V1, and so on, the corresponding vectors that we get better be orthogonal. And these are. Okay. So the problem now is that we got to use this formula up until we get to R. And R was 2 because we had 2 non-zero singular values. But our matrix U in this problem, so the issue is we're trying to find the singular value decomposition for A. So we're trying to write it in this form. And A was a 4 by 2 matrix, which means sigma is also 4 by 2. Sigma and A have the same size. U has to have the same number. Its size corresponds to the number of rows of A. So it's going to be 4 by 4. And V, its size corresponds to the number of columns of A. So 2 by 2. So the problem now is we've only found 2 columns of U, but A is supposed to have 4 columns. Sorry, U is supposed to have 4 columns because it's a 4 by 4 matrix. So the problem that we're faced with is exactly that. U is 4 by 4. We've only gotten 2 of the columns. So how do we get the other 2? How do we get vectors U3 and U4 that, well, we need them to be orthogonal because collectively all of these vectors in U need to be orthogonal. They also need to be unit vectors. And most importantly, U3 and U4 need to be orthogonal to U1 and U2. So there are two ways we can do this. So we have some options. So the first option is, so we want to get some vectors that are orthogonal to U1 and U2. So what we can do is we can put them in a matrix. So we can form a matrix that has U1 and U2 as the columns. So let's call this matrix B. It doesn't really matter what we call it. We probably don't want to call it A though, because we already had a matrix A in our problem. So what I'm going to do is I'm going to try to find some vectors that are orthogonal to the column space of B. Because if I can find vectors that are orthogonal to the column space of B, they're definitely going to be orthogonal to each of the columns individually. And that's what we're after. We want to find vectors that are orthogonal to both of these columns. So the column space of B is the span of the columns, the span of U1 and U2. Okay, so if I want to get some things that are orthogonal to the column space, let's take a look at what column space of B perp is. So using one of our theorems from our section, our chapter actually, on orthogonality, column space of B perp is the same thing as the null space of B transpose. So if we want to find some vectors that are orthogonal to the column space, in other words, they're definitely then going to be orthogonal to U1 and U2, we need to find an orthonormal basis for B transpose. So find an orthonormal basis for B transpose. So that's one way to go about it. Another way to go about it is to remember that U1 and U2, so in general, U1 up until UR, that is an orthonormal basis for the column space of the original matrix. So that's something that we saw in the last video. In fact, let's just flip to that. So in the last video, we saw that U1 all the way up until UR, they form an orthonormal basis for the column space of A, for the original matrix. So now we need to get some vectors that are orthogonal to those. In other words, let's look at column space of A perp. All right, so let's flip it back to our work. So the other way that we can do this now is we can get an orthonormal basis for the column space of A perp, because the column space of A contains both U1 and U2. And I'm trying to find vectors that are orthogonal to both U1 and U2. And I can do that by finding vectors that are orthogonal to everything in the column space. So I'm going to look at column space of A perp, because that consists of all those vectors that are orthogonal to everything in the column space. But column space of A perp, we know that that is the same thing as the null space of A transpose. So we have sort of two possible approaches. We can either put the vectors u1 and u2 into a matrix as columns and then find the null space of that matrix. Or we can go back to the original matrix A, if that's easier, and then find the null space of A transpose. We have these two possibilities. So let's do that for our example. So in our example, I'll do this by option 1 actually, but I can equally well have done it with option 2. All right, so I've gone ahead and done some of the computations. So B is going to be the matrix where I take u1 and u2 and write them as the columns. So u1, u2. In general with this matrix, I just want to keep going until I get to ur. And then I want to transpose that and then find the null space of B transpose. Because the null space of B transpose is going to be orthogonal to the column space of B. And that's what I want. So if we go through the row reduction, we end up getting, or I ended up getting these two vectors, u3 and u4. So are these the vectors that are going to work and that are going to make U an orthogonal matrix? So it turns out no, there's a problem with u3 and u4. They are not orthogonal. These are not orthogonal with each other. They are going to be orthogonal to u1 and to u2, but they aren't to each other. So what do we do when we have vectors that are not orthogonal, but we want them to be orthogonal? Well, we do Gram-Schmidt. So now we're going to do Gram-Schmidt. So I've gone ahead and done that work as well, but you should verify this. So if we do Gram-Schmidt, I end up with the following two vectors. The first vector stays the same, but the second vector now changes. I've decided to just stick with this labeling of the variables, so I've kept it just as u4, because I want to keep calling these vectors u's, because they're going to go into the matrix U ultimately. So u4 ends up being this vector. All right, so now are we done? Are u3 and u4 good? So still, no, not quite, but almost. They are not unit vectors yet, so we need to normalize them. So let's normalize these. So we need to normalize them. All right, and then after we normalize them, we end up with these two vectors. So this is what they look like after we normalize them. All right, so now we've gotten the remaining vectors of the matrix U. They are now orthonormal like we want them to be. So we're ready to write down our singular value decomposition. So A, we're writing it down in the form U times sigma times V transpose. So it's just a matter of writing down all the vectors that we have. And I've gone ahead and done that. Okay, so this first matrix right here, this is the matrix U. So notice that U3 and U4 are the vectors that we just got. They are the last two columns of this matrix U. This matrix in the middle, this is sigma, which we found earlier. And this matrix at the end, this is V transpose. It's not V, it's V transpose. All right, so if that's V transpose, what would V be? Well, V would be the transpose of V transpose. And in this case, this is a symmetric matrix. So V ends up actually being the same thing. So that's a cool coincidence. All right. So this is our singular value decomposition.